Hey guys, welcome to this video on determining the electric field for a disk of charge. The method that I'm going to use to do this is basically a continuation of the ring of charge video that was previous, so if you haven't checked that one out, check it out first. I'm going to do a conceptual map here of what it is we're actually doing, because I think that that's probably the most important thing in constructing the whole procedure so that you can apply it to different situations. Our very starting definition of what an electric field even is for a point charge is this equation. And this is one that we discussed quite a while back and I think makes a lot of sense for finding the electric field at some location R away from some source charge Q. What we did was, our first goal was to find the electric field for a ring of charge and located at a specific point. So essentially what we did was we said, well, a ring is made up of a bunch of points. So if I can show what I will call here a differential form of the point charge equation, then I can integrate the differential form and I can, in other words, add up all those little points to get a ring. So I'm going to change this equation here, just like we did before, to dE equals K dq over r squared. That showed me that it was a small contribution dq of the total q for the whole ring. I then did a bunch of substitutions, not only to relate to the actual variables used in the problem that was presented, but also to get the equation ready to be integrated in the most simplistic way. We then did some integration of this newly substituted equation, and the result was an equation that was E is equal to kzq over big R squared plus z squared to the 3/2. At this point, we're going to pick up on this video. And the idea again is to repeat the exact same process. We're taking an equation for some geometric component, changing it to a differential form, and then getting a new expression for what we're particularly looking at. So over here, again, my first step is going to be to try to get a differential form of the ring of charge equation, and that is going to be our first step in this process. And then we will do, again, substitutions to prepare this differential form for integration, and then actually do the integration, and we should have an equation then for a disk of charge. Now, visually speaking, what's happening here is we're saying, well, eventually to get to a ring of charge, we're adding up a bunch of points. In this case over here, we're adding up in order to get to a disk of charge. We're essentially saying that this disk is conglomeration of a whole bunch of rings of radius increasing all the way to our final value for the disk of big R. So you can see how this progresses from a point to a ring, from a bunch of rings to a disk. And that is the big idea of what we're doing. So let's get started on the process of going from the ring of charge step down all the way to the disk of charge step. So the first idea that I'm going to take here is my ring of charge equation, and I'm going to try to put it into a differential form. It's going to take a little bit more work than it did before, but let's start by saying that every ring that makes up this disk contributes a value dE to that point right there. So I'm going to change this to K times Z dQ, because each little ring is just a tiny portion of the total charge, which I should put here is Q. This I'm going to put over big R squared plus Z squared to the 3/2, even though I need to make some other adjustments. Now, all I've showed here so far is each tiny little contribution of the total Q is making a tiny contribution of the total electric field. I don't have to worry at this point about finding cosine components or anything like that, because this expression that I have for the ring of charge already inherently involves that. But what I am going to have to do is make some other adjustments over here. If we think about what's happening as we build in little rings into this picture over here, every little ring that's added to this drawing has a different value of R. So that value is changing as we work our way out to the total R at the very end. If you think about each ring is a fixed distance big R, or R from the center, in this case this outside one, big R, and that's contributing to this outer point. Well, the next concentric ring in is going to contribute a different amount, and is going to be a different R value. I'll call that one R prime. The next one in is maybe R double prime, and you can see that these values are changing as we work our way in to the center. In the previous step of doing the ring of charge, the ring was all equidistantly located away, and so we didn't have to account for the fact that R was varying. So what I'm going to do now is I'm actually going to change this R to little r, or lowercase r, because essentially what I'm saying here is that as little r varies, I will get a different R value here. So in other words, no longer is big R a fixed distance. This little r value over here is going to vary to represent this R value over here. And so I have something that looks like this. Now at this point, what I need to do is see if I'm ready to integrate. Well, clearly not, because I have my variable of possible variable of integration as dq, but I have a independent variable here of r, which again is this r that's changing as we work our way out. So what I need to do is change dq to match this, so it is dr instead. So we're going to jump over here to the side and take a look at a couple things. One thing I didn't tell you about this disk of charge is that it has a uniform surface charge density. So lowercase sigma is equal to Q over A. Alright, as this would be telling us that the surface charge density is constant. But what I want to do here is write Q in terms of area, because I know that area contains something about R, and that can help me get to that point. So if I write this as Q equals sigma A, and I change this to a differential form, so I make it dq equals sigma dA, I'm getting closer to having a variable of integration that's an R. Right now it's an A, and that's not the same thing, so I have to keep going. So if I do, again, expand out this dA, what I could write is dq is equal to sigma times 2 pi r dr. Now if you need help figuring out how did I get from there to there, just message me and we can go through that. So what I'm going to do now is replace this dq with all of this so that I'm able to make my next step in. So I'm going to go kz times sigma 2 pi r dr all over r squared plus z squared to the 3/2. Now I'm ready to do some integration. So if I integrate the left side, I should get my total charge value. And if I integrate the right side, I have to do a definite integral from the inside, which is 0, because I'm integrating with respect to r, all the way out to this outer point, which is located at big R distance away based on the dimensions given. Now there's a lot of things here that are constant, and I'm going to pull all of those out here. So k, z, sigma, 2, and pi are all constant, and I'm really integrating r times r squared plus z squared to the negative 3/2 with respect to r. So this is really the expression that I'm going to be integrating. Now what I'm going to do is I'm going to set all of this equal to a, just so I don't have to rewrite it 1,000 times during the steps, and I will refer to it as A until the end when I put it back together. All right, at this point, we're ready to actually do the integration. Now, what I want you to think about is that the procedure of setting up my integral is one step of understanding in this process. So I'm going to stop this video here and pick up directly in the next one with actually solving the mathematical component of this problem.